So welcome back, everybody, to our last talk today, but not our last session. So it's a great pleasure to have Eddy Chen giving this talk. Eddy will be pleased to hear that I haven't known him for 40 years. That would have been embarrassing. Anyway, but Eddy, welcome. It's lovely to have you here. The floor is yours.
Thank you so much, Simon. Can you hear me okay? Okay. So like earlier, my route to philosophy of physics was also through many worlds interpretation. I was a visiting student at Oxford for one semester in 2012, I believe, and sitting in seminars with Simon, David, tutorials with Chris Timpson, and that was my formal exposure to philosophy of physics. I found it very interesting, and although I didn't become a many-worlder, I always kept an interest in the theory. And Lab promised me today that in 1 week, I will have become a many-worlder, so we'll see. This talk and this paper version on arXiv is a paper about many worlds interpretation, although the title is not about many worlds, but you'll see the main idea, the main inspiration for this idea comes from the many worlds interpretation. Okay, let's start. The title of my talk is Strong Determinism. Now, determinism itself is a familiar concept, although it's tricky, right? As you might have expected from reading John Earman's book on primary on determinism. It is not my focus here. There's something else called super-determinism from quantum foundations, discussion of Bell theorem, PBR theorem, so on. It is less familiar and perhaps more puzzling. Again, it is not my focus here. So it's not determinism, it's not super-determinism, but it is strong determinism. That's the focus of this talk. My motivations are because this, I think, is an interesting idea that's not well understood and not well appreciated in philosophy of physics. It is less well known. It has received little theorizing. It has some extreme consequences for both physics and for topics in philosophy of science. It is surprisingly easy to achieve in an Everettian multiverse, but not in a way that one might expect. Okay, so my plan in this talk is to discuss what exactly is strong determinism, why is it interesting, and provide one example from many worlds, and discuss philosophical implications. Not the usual many worlds, by the way, but something different, as you will see. Okay, so strong determinism phrase comes from Penrose in his book, The Emperor's New Mind. He described it as follows. According to strong determinism, it is not just a matter of the future being determined by the past. The entire history of the universe is fixed, according to some precise mathematical scheme for all time. The basic idea is that it goes beyond determinism. It requires something more. My preferred definition doesn't depend on mathematical scheme, but requires fundamental laws of nature. Okay, let's start building to strong determinism by looking at determinism. How should we define determinism? So here are the basic ingredients for defining determinism, borrowing from John Earman's work. First, think about a possible world doubly, right? A possible world here just means a four-dimensional space-time and its material contents. A possible distribution of stuff on four-dimensional space-time. Okay, for many worlders, think of this as not a world, emergent world, but a universe, a fundamental universe, right? So a possible universe, doubly. Now, there's something else called the actual world, or the actual universe alpha. The actual space-time and its contents. Okay. Now we define omega t. For some theory t, fundamental laws in theory t give you a set of possibilities, set of solutions, set of histories compatible with the equations. So omega t is a set of possible worlds that satisfy the fundamental laws specified in theory t. Now, omega t may not be the law. The law may be very simple to describe, but omega t is a set of models, set of worlds compatible with theory t, the laws in theory t. And moreover, we can have definition of omega alpha being the set of possible worlds satisfy the actual fundamental laws obtaining in alpha, namely the set of all physically or nomologically possible worlds in the philosophy idiom. So omega alpha denotes a set of nomological possibilities. Omega t denotes a set of nomological possibilities according to theory T. Okay, where omega alpha picks out the actual set of nomological possibilities. Any questions so far? This is basic ingredients. Okay, now we define determinism as follows. Theory T is deterministic just in case for any two worlds in omega alpha, omega t, any two physically possible worlds according to theory T, if they agree at any time, they agree for all times. So the basic idea is that suppose you have a state space of histories or solutions to the fundamental equations in theory T. They don't cross in state space. Right? They are nice histories that never intersect. If they do intersect anywhere, that's a violation of determinism. If any two different histories intersect, diverges or converges, that means it fails determinism. Okay. And we say that alpha, the actual world, is deterministic just in case for any two worlds in the set of actual nomological possibilities, if they agree at any time, they agree for all times. This notion of determinism corresponds to what is called two-way determinism. I can define, say, maybe one-way determinism towards the future by saying they agree for all future times, right? But it's not the restriction I'm having in mind here. It's two-way determinism, going back to both future and past, applying for all times. So given the state at any time, this is compatible with only one development in the past and the future. All right, any questions? Good. Now given, okay, here's a picture again. It's as fancy as you can draw on Tixi. So you have 5, 6 histories, don't cross in state space. Deterministic theory T. This is the omega T. 6 histories. Using the same ingredients, we can define strong determinism in the following way. Theory T is strongly deterministic, just in case the set of possibilities, according to theory T, is a singleton set. The cardinality of omega T is 1. Its fundamental laws are compatible with exactly one possible world. The strong determinism is true just in case the actual world is strongly deterministic. Namely, omega alpha is a singleton set of alpha. So the actual history, the actual world, the actual universe is the only nomologically possible one. Okay. By the way, here I define strong determinism in terms of fundamental laws instead of mathematical scheme. I think it is less slippery than the definition of mathematical scheme is. And you see this actually comes out in our definitions of strong determinism for Everett. Okay, so here's a picture of strong determinism. Theory T, set of nomological possibilities, omega T has only one allowed history, only one allowed solution. Given the fundamental equations in theory T, there's only one solution, one history. Okay, so strong determinism, only one history. And this implies determinism, but it's not implied by determinism. Now, let me contrast strong determinism with super-determinism, another concept in foundations of quantum mechanics. The two are logically distinct. So super-determinism also goes beyond determinism, but there's some differences between super-determinism and strong determinism. So while typical histories according to super-determinism violate statistical independence, there can be failure randomization methods or conspiracies. Such a violation is not required on strong determinism. So this history can be compatible with randomization and scientific methodology, usual ways, and so on. Now, while there's exactly one physically possible world according to strong determinism, superdeterminism is compatible with having infinite many conspiratorial initial conditions or fine-tuned initial conditions or special initial conditions. So the two are logically independent.
So what is
superdeterminism? It is kind of a vague concept, corresponds to failure of statistical independence, which is an assumption in Bell theorem and various other theorems like PBR. Namely, you can have so-called free choices of the settings of experiments that doesn't depend on incoming electrons or photon settings. If you have superdeterminism, that doesn't have superdeterminism, right? I mean, that's a rough sketch. It's not quite what people like Hausenfelder and Palmer would describe. Okay, so what's interesting about strong determinism? Penrose gives one answer. He says, such a viewpoint might have some appeal if one is inclined to identify the Platonic world with the physical world in some way. Since Plato's world is fixed once and for all, with no alternative possibilities for the universe. He adds, I sometimes wonder whether Einstein might have had such a scheme in mind when he wrote, what I'm really interested in is whether God could have made the world in a different way. That is, whether the necessity of logical simplicity leaves any freedom at all. I will give you a different answer. On my view, strong determinism is interesting because it enables a strong type of explanation, strong type of prediction, and with implications for causation, counterfactuals, and principle of sufficient reason. I focus on the first two in this talk. So the first is about explanation. Usually, when we have deterministic laws, Schrödinger equation, Newtonian mechanics, so on, we have conditional explanations. Given the state of the universe at some time, or some interval of time, we can deduce from fundamental laws the state of the universe at any time. In that sense, it can be derived or explained by the state plus the laws. But it's conditional. Conditional on some initial data, or some middle data, or some final data. Strong determinism gives you strong explanation. It's unconditional. The fundamental laws alone entail the state of the universe at any time. Now, if strong determinism is true, every fact becomes subsumed under the fundamental laws. At the level of nomological possibilities or physical possibilities, nothing is left to chance, contingency, or randomness. There's not even a choice about microscopic initial conditions. The actual world, the actual universe, could not have been otherwise. It's a matter of physical laws. To use a God metaphor, God could not have chosen otherwise beyond the choice of fundamental laws. So if the actual world is only deterministic, then every actual fact can be explained by the fundamental laws alone. And if the fundamental laws are where scientific explanation ultimately stops, then strong explanation may be completely satisfactory, leaving nothing unexplained. This is kind of a rough idea. Of course, we'll be qualified in various ways. We can imagine even stronger type of explanation, you might think, where even the fundamental laws themselves are completely explained and found to be non-arbitrary, completely natural, maybe even a priori. That'll be a very difficult task. That is compatible with, but not demanded by, strong determinism or strong explanation. This explanation. Let's think about prediction. Similarly to explanation, on standard deterministic laws, we have conditional prediction. Given or conditional on the state of the universe at some time or some interval of time, we can in principle deduce, use the fundamental laws, the state of the universe at any time. But it's conditional. You have to have the precise micro initial condition or some state of the universe. Whereas for strong prediction, one can in principle deduce using the fundamental laws the state of the universe at any time. Naively, you seem to leave no room for uncertainty or ignorance. We might expect them to solve many of our practical problems, such as predicting the outcome of the next election, midterm election coming up, without needing input from the exact microstate of the universe right now. For Laplacian demon, that means the demon will have unlimited predictive power without even needing exact microstate. But we, as agents like us, may have epistemic limitations. There can still be, or we can still have, meaningful notions of uncertainty or ignorance by self-location, for example. Now, strong determinism is also interesting in itself. So you might think, what does a strong deterministic theory look like? What does a strong deterministic world look like? Are we living such a world? And can we find out by doing experiments or observations? And short answer is no, probably not. And it could be the case we're living in such a world. Let's think of some examples. So you can think of some mundane examples in which the laws completely fix the position of every particle every time. That's not very interesting. It may not actually be very compelling. We can think of some mathematical schema or mathematical equation that fix the pattern of the entire spacetime. I think a more realistic case comes from Everett or Manuel's interpretation. Penrose continues in the following paragraph. He says, as a variant of strong determinism, when we consider the Manuel's view of quantum mechanics. He says, according to this, it will not be a single individual universe history that will be fixed by a precise mathematical scheme, but the totality of myriads upon myriads of possible universe histories that will be so determined. Despite the unpleasant nature, at least to me, such a scheme and the multiple problems and inequities that you presented with, it cannot be ruled out as a possibility. So Penrose thinking, the Everettian quantum mechanics, Everettian multiverse, considering each representation is described by a wave function evolving unitarily in time, is a case of strong determinism. On my view, however, it is not. The theory of Everettian quantum mechanics in the wave function picture usually allows infinite many nomologically possible choices of the exact initial wave function of the universe. Depending on which one we have, they'll have different, slightly different multiverse histories. Hence, infinite many possible histories of the multiverse. So it's not only deterministic by the perspective of laws of nature. However, there is an Everettian theory that is strongly deterministic, on my definition. It is different from, but inspired by, what's called Everettian Wentaculus. It's the idea of combining Everettian picture of the unitarily evolving wave function with certain idea of how to understand arrow of time, with the past hypothesis and cyclic postulate. So it is not the same as Wentaculus, but it's called Everettian Wentaculus. So on this picture of Everett, the multiverse is not described by a pure state, but by a density matrix, a mixed state. And still you have inertial dynamics by the von Neumann equation, but a new law that selects a unique density matrix of the entire multiverse at T0. Okay. So the Wentaculus, Everettian Wentaculus is one version of the Wentaculus, and developed this idea in a few papers published and also on arXiv. Now, let me first review the Wentaculus picture of Everett. So Everett, usually you can think about a wave function evolving by the Schrödinger equation or some kind of linear unitary equation. You add the past hypothesis to get causality for the arrow of time or entropy gradient. Right? At a temporal boundary universe, the wave function psi 0 is constrained by the past hypothesis to lie inside a low entropy macro state such that this is corresponding to some low dimensional subspace, the total Hilbert space. So in the classical picture, you have the past hypothesis selecting a small region in the phase space. Think about Penrose diagram, small region in phase space. Here is a small subspace in the total Hilbert space. That is where the wave function must lie. Now, because not every wave function compatible with past hypothesis is going to be entropic or increasing entropy, you have the following cyclical postulate postulating some kind of product distribution over possible wave functions compatible with the past hypothesis. Now you have three postulates, all fundamental postulates, maybe called laws of nature. Okay. Now even with a restriction to a low entropy start, this Wentaculus picture of Everett still admits many possible choices of the initial wave function. Can we do better? Can we narrow down the initial choice to exactly one? Can we somehow constrain initial state so much it becomes a single state? I think we can. I propose that we use the past hypothesis to pin down a natural initial quantum state in the following way. The first step, however, is to reject the idea that the multiverse or the universe must be described by a pure state. So allow the quantum state of the universe or multiverse be given by a density matrix rather than a wave function. It does not arise out of ignorance or entanglement. And second, we observe that there's a natural density matrix in the low dimensional subspace, HPH. The low dimensional low entropy subspace according to past hypothesis. What is the natural density matrix? It is basically the canonical one, the natural choice, the projection operator onto the subspace divided by the dimension of the subspace. Normalized projection, the density matrix. Here I'm assuming the Hilbert space corresponding to the low entropy subspace is finite dimensional. Right? So HPH is finite dimensional subspace. So this corresponds to a low entropy density matrix. It is like the natural one given the subspace. It is as simple as the subspace itself. So here we have the Everettian Wentaculus, only two postulates. The first one replaces the Schrodinger equation involving wave function with the following. We have a density matrix evolving time by the von Neumann equation, linear, deterministic, unitary. But the boundary conditions given by the initial projection hypothesis, a new law that's like the past hypothesis, but it's more severe constraint. It says a temporal boundary of the universe density matrix is and must be the normalized projection onto this subspace. So WT0, the density matrix equal to the normalized projection onto the subspace. So W is my symbol for density matrix. That's why it's called a Wentaculus instead of Mantaculus. As you're wondering. Okay. Observe that since there's a single or unique nomologically possible state at T0, we no longer need a statistical postulate. This state will be entropic. Now observe that given the fundamental laws, the von Neumann equation, plot initial condition given by the initial projection hypothesis, there's exactly one physically possible history of the entire multiverse. So I'm thinking now both postulates here are considered fundamental laws of physics in the theory. So only one physical possible history given the two laws. So the set of normalized possibilities of theory T is exactly cardinality equal to 1. Therefore, the Everettian Wentaculus is strongly deterministic on my definition. What does the world look like on the picture? People are not used to thinking about density matrix for the whole multiverse. Actually, it corresponds to the same way as how to be a realistic quantum state in general. In the case of pure state, you have different options, right? You have the high-dimensional field picture. You can have a field living on 6n-dimensional fundamental space, or a multi-field that assigns points to value to every 2 points in 3-dimensional configuration space, fundamental space, or multi-field in a 3-dimensional space. Or it can be a space-time state realist, like Wallace and Timpson, and think of this assigning properties, big states, to regions in 4-dimensional space-time. We can think of this as Carroll and Singh, method Everettianism, as a geometric object in infinite-dimensional Hilbert space. Or we can think of this as a law concerning distributed matter in space-time, how space-time matter evolves. Okay, so there are more options here. Now, there's no fundamental or nomic contingency or possibility beyond the actual one. If notions of contingency, chance, probability, counterfactuals, causation make sense in the world, they have to be emergent at the level of branches in this multiverse. And we also need to appeal to something like decision theory construction, Wallace Deutsch, or self-locating reasoning. So McQueen, Weidman, Siebens, Carroll, and others. By the way, Eugene Chua and I are working on this paper together, branching and the Born rule in the mixed state Everettian multiverse. So the basic idea is that we can extend understanding decoherence, branching, justification of Born rule from the pure state case to a mixed state case. Pretty straightforward here. Okay. So on the Everettian Wentaculus, there is no need for any notions of probability or typicality at the fundamental level of physics. And this compares to favorably with David Albert's conjecture of GRW, eliminating system mechanical probabilities, and David Wallace's conjecture of simple path hypothesis, eliminating other kinds of system mechanical probabilities. So there's another route we can get rid of fundamental objective probabilities in system mechanics. Okay. Now, so this shows that a strongly deterministic theory is not difficult to find. And Everettian Wentaculus provides an easy route. At this point, you might wonder, can we get it more easily, more trivially perhaps, more straightforwardly? You might have thought of this already. Come on, think about strategy A. You have any deterministic theory. You can specify the actual microstate of the universe as a fundamental law. At T0 or T1, T2, doesn't matter. But specify the fundamental microstate at some time, you get strong determinism straightforwardly. Or strategy B. When in theory 2, specify the entire space-time its contents, the whole manifold, as a fundamental law. The problem with these two approaches is this. In general, the two strategies will make very complicated laws that don't explain very well. In contrast, the past hypothesis is supposed to be a simple law that can be described in relatively coarse-grained, simple, and macroscopic language, informationally not burdensome. And similarly, the initial rejection hypothesis is not going to carry more information than the initial subspace carries. So the idea is that the Wentaculus laws are going to be simple laws that can make a strongly deterministic version. Where this two strategies is going to make very complicated laws, but not very explanatory. Now, is Everettian Wentaculus empirically adequate with respect to data confirming quantum mechanics and statistical mechanics? I assume so in this talk, in this paper. But it is a subtle issue. There's a probability problem to solve. Now, assuming this, we say that Everettian Wentaculus is non-deterministic, and moreover, it is empirically equivalent to the Everettian Wentaculus, or any way of thinking about Everett in a time asymmetric universe with conditions plus some randomness condition. And arguably, and David Wallace will argue it is not the case, but arguably, Everettian Wentaculus is empirically equivalent to Boolean versions of Wentaculus, Wentaculus, and so on. So in a sense, every quantum theory is empirically equivalent to one that is strongly deterministic, namely the Everettian Wentaculus. In a time asymmetric universe like ours, with quantum data and strong error of time, we cannot find out whether strong determinism is true or false by appealing to data, experimental observations. We have to appeal to super-empirical virtues. And in that case, they might actually favor strong determinism over non-strong determinism. In conclusion, strong determinism means the set of normalized possibilities, the singleton set, namely set of alpha, the actual world. It is interesting for explanatory and predict reasons. The Everettian Wentaculus is one sort of realistic example, the simple theory that realizes strong determinism. So it shows that strong determinism is surprisingly easy to achieve, but it may not have the features we expect. And moreover, given empirical equivalence, we can never empirically rule out strong determinism. We must rely on super-empirical virtues. And in the end, it may actually favor strong determinism over non-strong determinism. Okay, here are some papers, some archived and published that are related to this project on laws and quantum mechanics, density measured realism, and Wentaculus. Thank you. This is the end. I have to say I'm very jealous, so if there's a very difficult question, I'm just going to pass.
Yeah, so really interesting. Okay, so given the fundamental laws of the Everettian Wentaculus, you say there's exactly one possible history of the Everettian multiverse. Of course, that raises the question, what explains the postulates? Right, so like on my account, we explain the features of quantum mechanics in terms of something more basic, but you're taking these to be postulates. So in particular, what explains the natural density matrix postulate? Is it supposed to be the fact that it's natural? And if so, I mean, shouldn't we have learned from like the failure of supersymmetry and beyond the standard model physics that naturalness arguments are bad, right? That there's no reason to think that the universe is natural in the sense of being the simplest, conforming to the simplest theory possible. That's the question.
Yeah, thank you, Marcus. So, like I said, you can demand a stronger version of strong determinism where we have a sufficient explanation for even the laws themselves. But I take it that if we take laws as a starting point in scientific explanation, then we have reached the bedrock of explanation. Of course, we can ask further metaphysical explanations, or maybe super empirical explanations, or a priori explanations. But I don't think that's quite possible. Perhaps I can give some kind of naturalness considerations with simplicity and so on. And that's, I think, what's driving the super empirical virtues here, right? Suppose we want to have a simple description of reality, simple law, simple constraints, then we're going to reach for certain kind of considerations of simplicity. I do think that those notions should not be overplayed, right? So there can be ways to exaggerate their importance beyond empirical adequacy. Empirical adequacy is always the star, the king of constraining the theory. But there's always so much data we can collect. And even if at the end of humanity, there's always limited data we have reached. So we cannot possibly exhaust all possible data to limit what kind of universe we live in, or what kind of laws that explain the universe. So we have to appeal to some super-empirical virtues in the end. Thank you.
So there's a subtle move that comes between something like the Albert framework and your Wentaculus framework. So they're both using the idea of Boltzmannian macrostates and a notion of entropy defined in terms of that. But normally in this Boltzmannian approach to statistical mechanics, then the macrostate decomposition is supposed to be some kind of higher level notion. Sometimes it's related to the macroscopically distinguishable, so almost a pragmatic aspect.
Right.
Sometimes it's related to what the higher level emergent dynamical laws look like.
Right.
And there's something like, at least on one approach to thinking about what we're supposed to put in our fundamental physics, higher level notions like that shouldn't be in our microphysics. Now that's not a problem for Albert, because the past hypothesis is just the hypothesis that whatever cosmology spits out will in fact spit out a state that sits in a low entropy Boltzmannian macrostate. It's not, as you know, it's not correctly glossed as just saying it's a law that the universe starts at a low entropy. It's supposed to basically there are
More detailed description.
Exactly,
Yeah.
and it so happens that principle delivers
Yeah.
something that sits in the low entropy. But that's not true for your Wentaculus framework, of course. You're saying that it's a law that the initial state is a normalized projector onto a low entropy Boltzmannian macrostate. Could you say a bit about how you want to think about the sort of top-down aspects?
Right, good, thank you. So yeah, in my description of Wentaculus, I wanted to highlight this, but I didn't have time. That is, the partition, the decomposition of a macrostates is going to be given by some choice of C parameters, where C is sort of conventional parameters, like coarse graining cells and correspondence function of microstates and set of microstates to macrostates. There's going to be dependence on the language we use. There's going to be vagueness of the partition. That's something that we talked about before. So regarding the vagueness issue, and this may be one aspect that supposedly we shouldn't have vagueness from the laws. Now I think about it, actually it's not incompatible with the notion of fundamental constraints or human laws, or either human or non-human laws, to think that laws have to be exact. So I wrote a paper on this, on fundamental normative vagueness. The difference in the Wentaculus picture is that actually the vagueness can be eliminated without objectionable kind of arbitrariness. So the idea is that the way of eliminating vagueness on the past hypothesis, the Wentaculus or wave function picture, is that you say, stipulate there's omega 0 or some precise boundaries of low entropy states that's out there in nature or given by the laws. We don't know which one it is, and it can be fuzzy and borderline cases and so on. But it'll be arbitrary in the sense that it become untraceable, in the sense that most states compatible with that one feel no difference whatsoever on the boundaries of this state. Unlike, say, arbitrariness and constant of nature, that will make a difference to most states compatible with the original version. In the case of Wentaculus law, the arbitrariness is, of this kind, is gone. Suppose there is an arbitrary, sharp density matrix corresponding to some arbitrary sharp subspace. Then this one is arbitrary, but not objectionable in the sense of the past hypothesis, because what this is makes a difference to reality, to the actual physical state, and say to Everettian branches and to Bohmian particles, Yardley collapses. So this actually makes a dynamical impact on the world, maybe a slight impact. So regarding vagueness, I think this is an improvement.
But then I've slightly lost track of, I mean, that sounds reasonable, but I've slightly lost track of what the connection is now between the low dimensional subspace and the
Right.
and the Boltzmannian subspace. I mean, provided that low dimensional subspace is inside the Boltzmannian subspace, it's got no obligation to saturate it. I mean, if we talk about this over lunch, if actually my initial projection hypothesis that the density matrix is the one-dimensional projector onto the Davis vacuum, say, I mean, that's not
Right.
a macrostate in your sense. It's a but that's a uniquely specified pure state that will do fine. Is that okay in your framework?
No, I was assuming that the initial density matrix is not a pure state and corresponds to something like a projection onto a Boltzmannian law entry macro state. But which one exactly it is like a constant of nature. That is, our measurements don't really pin down any precise value for constants up to some points, but there is effect in nature. So this is the Boltzmann description of macro state and high-level structure is like a ladder that helps us to pick out this fundamental constant-like thing. But in the end, the fundamental law is not those descriptions, but the density matrix itself.
Oh, okay, but then slightly to my surprise, I'm starting to sympathize with Marcus's concern, because it feels as if you don't dodge the irreducible connection between the high level and low level by precisifying it. I mean, let's suppose that I wanted to have as a law of nature, as a microphysical law of nature,
right,
that the distribution of the stars resemble Mickey Mouse. Now, that seems unsatisfactory in a scientific theory. Now, it doesn't seem that I resolve the unsatisfactoriness by saying, well, of course, it's fundamental, so there's some precisification of Mickey Mouse that's exactly picked out here. There's still some weird feedback loop between a high-level way of specifying things and what the low-level physics looks like.
I was thinking there will be a precise and simple way to describe it in the subspace that's perhaps vague in some way. And that simplicity is not going to be in a micro language, but there's going to be some constraint of naturalness of the language which you use to describe that function. Perhaps some distribution function on some coarse grain variables, but that's going to pick out a vague class of precise subspaces, among which one of them is the actual one, the actual correct subspace for the density matrix. And that will be the criterion for simplicity. You're not insisting on simplicity or naturalness of the fundamental language here.
We have to start getting...
Yeah, I know. Yeah, it's kind of substantive issue that's tricky. I didn't really have time to address this. Thank you for the question.
We are running a bit short of time, but let me have one more question. Sure. Eric, I'm sorry, before
So there was some ambiguity in how you laid out the picture. If one uses the I think what are more or less the standard background assumptions in the kind of work you're talking about, then the Hilbert space is a Hilbert space of matter fields, and they're living on some fixed fixed background spacetime. But then you have to specify but that by itself won't suffice to fix the global structure of the spacetime.
Yeah.
So you're going to have to throw in some other laws to specify the global spacetime structure. You might want to try and get around that by saying, no, in fact, the Hilbert space and the state function are really, space. It's quantum gravity.
Sure.
But then you're pretty much stuck with something like canonical quantum gravity, in which case you're going to, in fact, it will be or it should be empirically falsifiable. I mean, we should be able to empirically rule out canonical quantum gravity as the right quantum gravity.
Yeah.
So it seems like you're stuck with either saying, in fact, things are going to look explanatorily a lot more complicated, because specifying why this particular, why, for instance, we want to stick with globally hyperbolic spacetimes, there's going to be some non-trivial story to tell about that, or else you're going to be forced to say, no, in fact, it is empirically falsifiable.
I see. No, I don't disagree with that point. I'm thinking that in this picture, I have the simplified idea. Set aside quantum gravity issues, how to quantize gravity, how to have a quantum theory of space-time, to think about ordinary quantum mechanics without getting into space-time issues, and think about, okay, for this domain, can we have debate about strong determinism? Yes, we can. Now, suppose we have a theory in which quantum is not fully quantum in the end, then the whole issue has to be revised, like we don't have a Hilbert space, then what do we do with density matrix, right? So yes, in that sense, it's falsifiable because we might not have a quantum theory in the end. Yes, of course.
But then you still need to specify global spacetime structure.
Right. But in this case, think about fixed global spacetime structure already, right?
But that would be a law of nature under picture.
Right, I see. So you're thinking that it's compatible with many different spacetimes? So, yeah, I'm not sure to think about that. I was thinking you can set us the bracket of space-time degrees of freedom and just see what happens for the quantum mechanical theory. Okay. It's all holistic for you, Eric.
Okay, so strong determinism may have suddenly failed for the Wentaculus, but it applies to me and all of us. I've been applied So in that light, John.
Yeah, I mean, that's a brilliant idea. It's a brilliant idea that there should be laws of physics for the initial, for what the quantum state is. However, as an older person, I should point out that Hartley and Hawking already did
Right.
this back in
Right.
1982.
That's
And they-
right.
They have a particular proposal for a pure state to
Yes.
given by a path integral with, no other boundary.
Yeah. Mhm.
So, I mean, of course, they don't use quite the same words, but I mean,
Mhm.
obviously, at least if they accept that quantum
Right.
mechanics is deterministic, I think Hawking does. Hartle, I'm a
Yeah.
little bit uncertain about.
Yeah, yeah.
But then certainly if this is unique state, now, of course, you're doing a different one, so it's interesting to propose. I mean, because
Sure.
there are some, I mean, Hawking one did, of course, include quantum gravity.
That's
from
right.
what,
Mhm.
from what we knew of it. So it's, in that sense, it's gone further than this.
I
But on
see.
the other hand, there are some technical problems with it, because it seems with the
Mm-hmm.
cosmological constant that the Hartle-Hawking one tends to predict an empty universe.
Uh-huh. Uh-huh.
So it's, anyway, there's some controversy
Right,
that I have
right.
with Susskind and I
I
have
see.
with them. So it's worth it pursuing other things, but I think it'd probably be good to remind that you're not the
Yeah,
first to
yeah.
propose a particular. And Vilenkin also did it's out of tunneling state, and I think Starbinsky had some variant of that. So there has been other proposals for, I have my own, a symmetric bounce
okay.
thing, but
I see.
it's not as elegant as the Hartle-Hawking one.
Uh-huh. Thank you, Don. In the longer version of the talk, and the paper version, I do mention the Hartle-Hawking state. And it's one thing I've been puzzling about, whether they intend the description to be a fundamental law, a simple law, or just as a description of the actual physical state of the universe. And I couldn't really tell from their writings what they mean by a nominally necessary state, or just basically a description of the actual state. So in that sense, I wasn't sure that they really intend to have strong determinism.
Yeah, well, it's a question, of course, whether you say the laws are descriptive or proscriptive. I mean, that's a philosophical debate that people can have. But I mean, if we just say it's a description, then, I mean, you could say, well, here are the laws that describe our universe.
I see. I was thinking that that state itself cannot be described in, I mean, it's a simple formal structure, right? That integral over all possible Euclidean histories, but specifying that history set, says for each history it's going to be a very complicated formula. So it's not clear to me how to say that law in a concise way in every detail, except in formal structure, in this brackets of the Euclidean histories.
Yeah, there may be a similar difficulty trying to figure out.
That's true, yeah. Ultimate subspace, yeah. Mhm. Right,
Yeah, there's enormous technical difficulties.
right.
It's I don't want to discourage looking for other states,
Yeah,
but
yeah.
just remind people that yours is not the first.
Yes, I do that in the paper version. Yeah, thank you.